So last time we stopped at after covering the small signal analysis applied on the diode, and I just want to re-stress that. Okay, so the idea of small signal analysis is really critical, because if we understand it here, we will apply it on the MOSFET and BJT as well. Okay, so really what we did was find the DC operating point. Find the DC operating point of our circuit from this equivalent circuit, right? So from the equivalent circuit without this source here, right? We just had a, actually let me just draw it, draw the equivalent circuit again. Yeah, because we have to have a resistor in there. So from the equivalent circuit of here, which we can draw again as, right? So we had this equivalent circuit. So we started with 0.7, but let me just keep it VD. Sorry. So in general, we had this power supply, VDD, and a voltage across the diode, VD, which we modeled as this battery, and we had this resistor here. We found the current flowing using, again, we had two equations and two unknowns. Remember? So here is you don't know the current, and you don't know the voltage here across this device, right? So we found another equation in the same two unknowns using the diode exponential equation, which had VD and ID unknowns in it as well, and we applied either iteration or graphical methods to find the operating point. So we found this operating point. After we found the operating point, using the VD and ID that we found from the DC operating point analysis of the circuit, then we said, okay, this source that, my power supply that's here in the original circuit also has some ripple, right? It has some ripple. If this was a linear circuit, I can use superposition. I can first build the circuit with, the DC source by itself and solve the circuit, which we did here. And then I can put the AC source that we had, which, it was a ripple of plus minus 1 volt sine wave, I think. And then, theoretically, I can build the circuit and solve. So we didn't know what to put here. We know that the diode model for DC steady state is this reverse voltage. It's a forward voltage, it's called, right? So we didn't know what the diode model is for small signals, higher frequency signals. We did not know what it was. So we realized that, okay, when we did the analysis of the equations, we realized that this was nothing but a resistor model. And it came from this equation that we had here. The final equation that we came up with was, that the total diode current was equal to the DC steady state operating current plus some gain multiplied by this input voltage variation that we have applied to the diode, right? So this gain happened to be equal to I over V. We know that what's Ohm's law is equal to what? V equals I R. So I over V is equal to 1 over R. So this I over V is equal to 1 over R. So I have ID is equal to 1 over RD times VD, right? What is this? This is VD equals ID times RD. Just Ohm's law, right? It's just Ohm's law, but with a specific value of this resistance. This value happens to be the slope. This ID over VD at the operating point happens to be the slope of this curve, right? At this point, at this operating point here, I will do this. At this operating point, I take this straight line. This straight line has a slope. Delta y over delta x is the slope of any line, right? Delta y is current. At this point, it's delta y is what? Is ID minus 0. ID minus 0, that's my delta y. And my delta x is VD minus 0, so it's basically ID over VD. That's that ratio that we had in that equation. Okay? So hence we said that we can model this diode for the small signal. Again, and we said it's limited to small signals, meaning the voltage this ripple voltage that I'm applying at the input has to be less than or equal to 5 millivolts. Right? Because V over VT this V over VT has to be smaller than 1. We said, so that's, 5 millivolts is the limit. So we said that this allows us to do this superposition. And this is called the small signal analysis, right? So we did a DC operating point analysis, and then we did a small signal analysis given an assumption. And we will do the same for MOSFET. We will do a DC analysis, operating point, and we will do an AC signal analysis around that. And we will also have a constraint on the voltage that we will derive in the MOSFET chapter. Same thing with the BJT. We will do a DC operating point analysis to find this DC operating point. And then we will do an AC analysis, AC small signal analysis with a physical, physical limit on the signal based on the physics of the device as well. Just that the device physics is different. Here, it's V over VT that we limit it to less than 1. In the MOSFET, it will be something else. In the BJT, it will be something else. But it's the same. And all of them, what did they do? They amplified the current or amplified the quantity. So here we had the voltage at the voltage ripple at the input, right, of a certain value. This voltage ripple at the input caused higher current. Higher current caused a larger drop on the resistor that's in the path, and the result was what? On the diode model, and the resistor that's modeling the diode, the result was a lower variation in ripple voltage, right? That's what we have in our example. In our example, we had an input voltage with a peak-to-peak ripple of 1 volt, right? What did we end up seeing at the output? Across this diode resistor, we ended up seeing 2.68 millivolts. So we had a supply of 10 volts with a plus minus 1 ripple, plus minus 1 volt ripple. So it was 10% ripple. And then this 10% ripple of 1 volt became 2.68 millivolt ripple, right? So this 2.68 millivolts is about 0.4% of the output voltage, which is about 0.7, right? So it's so much reduction in ripple voltage here that we got, right? And this is what we will get with the different amplifiers. So this is sort of an attenuator, if you want. It amplified the current and dropped that across the series resistor before the diode, so that we can limit or regulate the voltage on the diode. And that's the application that we will use for this in the diode application. In the MOSFET and BJT application, we will use them to increase the value of our signal. So here we have our signal was what? Our signal was this VD. We attenuated it so that we can apply it in voltage regulation. I cannot really put a signal and amplify it using this diode application, using this just a pure diode. That's where we will come in and add, try to see what we can do with a MOSFET and a BJT device here. But the idea is the same: DC operating point analysis, then small signal analysis. Yeah. So that being said, we just go. So here in this section they just discuss, they formally discuss now the voltage regulator application. So before they were not discussing the voltage regulator application; they were just saying, fine, we have a diode, DC operating point, and the AC small signal analysis, right? So the application of that is really in the voltage regulation. What is voltage regulation? Voltage regulation is trying to fix an output voltage in the presence of what? In the example, it was in the presence of input voltage variation. It can also be in the presence of load variation, right? Remember, if you have a load here on any circuit, if you have a black box here and you add the load, if you are actually regulating the voltage here to 10 volts, what's going to happen to the current if the load changes? The current will change. If the current changes and your source here has an internal resistance, then there will be a variable voltage drop across this resistor if the current changes, right? So that's why we want this in an amplifier. We want this to be 0, because otherwise it's going to be very difficult to regulate this to 10 volts. You will have to be changing the input voltage all the time, your source voltage all the time, right? So if you are, and that's what's happening actually in the power system as well. In the power system, when we are actually fully loading the power system, if you've studied, if you've taken 338, the machine scores, or if you have ever played with a motor, if you played with a small DC motor, and you try to, can you hold it with your hands? You can try. You can try to hold it with your hands. And what happens when you hold the DC motor with your hands? The DC motor shaft? You've never tried playing with a small DC motor, Lego, the Meccano and stuff. What will happen? It will slow down. If you hold the shaft with your hand for the same battery input voltage, for the same battery, then what's going to happen is it will slow down until maybe it stops, right? So, and similarly, the power system is the same. We have these synchronous generators that we have in the power system. When we keep loading the system, their speed goes down, right? So when the speed goes down, the voltage goes down, right? So what do people do in the power system? What do the power engineers do? Open the gas valves. If you open up the gas valves or the fuel valves or the coal valves, whatever it is, it drives more fuel into the system. The turbine, that's the steam turbine that is running the generator, will speed up, will add more torque. Add more torque and hence speed up the generator, bringing back the voltage to where it is. Okay? So, and that's how they regulate voltage there. But if you want to regulate voltage in an electronic circuit, let's look at what we can do here. So this is an example where we have this, circuit. This is the input is 10 volts. Fine, plus minus 1 volt is depending on what they ask. They have many requirements here. But consider the circuit shown. So you have a string of 3 diodes, and you want to provide a constant voltage of 2.1 volts, right? It makes sense that if I'm assuming that my diode is regulating at around 0.7, I put 3 diodes in series if I want to regulate a voltage of 2.1 volts. You want to calculate the percentage change in this regulated voltage caused by a plus minus 10% change in the power supply voltage. That's what we did in the previous example, right? But in that case, we had one diode, and we had a plus minus 1 volt change in the input voltage. The other thing is that we didn't do in the previous example now is B. Connect a load across. In the previous example, we just looked at the voltage across the diode. We did not look at, so we had a model in the AC small signal analysis, we had a model that looked like what? Like this. This was our diode. But what if I do this? Add a load here. What will that do? It will actually divide the current here. So something will change here. So which means that if you divide the current, that means that the current here will be less. So the voltage drop here will be different here, right? So versus the open circuit condition, right? That's the moral. That's the moral here. Yeah. So we will see here what they want. So let's see. Let's try to go through the example. So here, this is our circuit with and without the load connected. This is my output voltage. So with no load, our load is not connected. How do I calculate the string, the current flowing in this diode string? I take my 10 volts minus 2.1, which is my 0.7 times 3, divide that by 1 kilo ohms. Right, I get 7.9 milliamps. Right, so. But first they didn't. So they're asking for first. Okay, so they want you to first calculate remember your DC operating point. First, you have to calculate the DC operating point will not consider the ripple, right? The plus minus 1 volt is a ripple, right? We will not consider that with the DC operating point, right? So first, we calculate the DC operating point, 7.9 milliamps. So it means that I have a circuit that looks like this. This is my resistor R. This is my 10 volts, and this is my forward voltage, 2.1 volt. I calculate the current here as 7.9 milliamps. Right? This is my current flowing in this circuit here. So that's my DC operating point analysis. Now I have to do the AC operating point analysis to look at the effect of the plus minus 1 volt ripple. Correct? How do you do that? You take your 10 volt as well, same resistor. Now you have RD here. This RD is equal to the VT voltage divided by the current that you found from your DC operating point analysis, right? So that is equal to it happened to be 3.2 ohms here. That is for one diode, right? Since I have 3 diodes in series, we would multiply that by 3, and I have a 9.6 ohm resistor that I have seeing this plus minus 1 volt variation. So if I would like to look at what is the maximum variation across the 3 resistors, what do? I have 2 volts, which is the peak-to-peak voltage variation. Now I only have now my small signal circuit. What does my small signal circuit look like? It's the AC source, right? This is my RD, which is times 3, sorry, and this is my R, right? This is 9.6, and this was the 1 kilo ohm, right? Right. So what is the voltage now due to the voltage on the diode due to the ripple? It's the maximum ripple voltage is 2 volts, right? And then it's a voltage divider between the 9.6. This is the 9.6 ohms, and this is the 9.6 ohm plus the 1 kilo ohm. Okay? Voltage divider across these 2 resistors. Okay, we're good. Next, what do they do? Okay, then we add a load. Originally, we had how much current flowing through? We had 7.9 milliamps from the DC operating point. Do we agree? So I had 7.9 milliamps. This is my chain of diodes that had 7.9 milliamps flowing through it. Right? When I calculated my ripple, I did what? I had basically this 7.9 milliamps was flowing through. Initially, my 7.9 milliamps was flowing through my device, correct? So if I had 7.9 milliamps flowing through 9.6 ohms, that's my original configuration, right? Now, they're saying that we have a load resistance of 1 kilo ohm is connected across the diode string, and it draws 2.1 milliamps. They told you it draws 2.1 milliamps. So what is the current that is now flowing through your diode string?
7.9 minus 2.
Yeah, so it's about 7.9 minus 9 minus 2. It's 5.8 milliamps. So 5.8 milliamps is now flowing through. So this is now you agree that this is now your new DC operating point? You've changed the DC operating point, right? We have changed ID. Since we've changed ID, then we've also changed VD. So you can go back and calculate the different ID and VD. But basically, we have a 2.1 milliamp difference in current flowing, right? This 2.1 milliamp, if you multiply that by the resistor that is flowing through, you can take, of course, 7.9 times 9.6, and you will have a voltage.
Why did they put negative 25
Negative because it's reducing, because you have 7.9 milliamps originally flowing, and now you have 5.8 here and 2.1 milliamp here, right? So you have reduced the voltage flowing through the diode string by 2.1 milliamp. That's why they put a negative sign. So the delta V, is it the positive delta V or is it the negative delta V? That's all it's saying here, right? So it's 2.1 multiplied by this total resistance that you have. It's approximately 20 millivolts, right? So now this 20 millivolts. How many diodes did I have? How many?
3.
So if on all 3 diodes, the voltage will change by 20 millivolts. That means that each diode, the voltage will change by about 6.8 millivolts, right? Which is more than 5 millivolts. So our small signal analysis work will not be valid in this case, right? So they tell you that you cannot really apply this signal and consider that this will work. Yeah. So since this implies that the voltage across each diode decreases by 6.7 millivolts, our use of small signal model is not entirely justified. Nevertheless, the calculation of the voltage change using the exponential result gives us 23 millivolts, which is not too different from the approximate value obtained from the incremental model. Yeah. So they're just telling us here that you cannot use your small signal analysis in this case. Right? So you will not, the result is your regulation will not be modeled by that small signal analysis model. Right? That's the result here. Okay? For the previous loads, it is. For this one, no. Okay. Operation in Zener mode. So we talked a lot about Zener mode, so I will. So it's called Zener mode or breakdown mode, and the model for the Zener is very similar to the diode model, except that no, they add these two things here to the diode model. Okay. So, but am I operating in the forward or reverse mode? Operating in the reverse mode. So remember the diode model was this, right? The voltage that was opposing the current flow was modeled this way, right? It was a voltage source, 0.7 volt, that was opposing the current flow. So only when you've put a voltage on the anode side higher than 0.7 volts than the cathode side, then you can forward bias the diode and the current can conduct. So what did I do here? Current is in this direction. No, this is wrong. You guys are not awake. Huh? It's opposing current, right? So it's like this, right? So it's in the direction that opposes the 0.7 volt is in the direction that opposes the current, right? That's because I'm operating where? In the forward mode, right? In the forward mode here, it's the voltage that's beyond which you have to that current will flow. In the reverse mode, it's a bit different, right? In the reverse mode, the model of the Zener diode will look like this, right? So where this flat symbol is, it's opposite the diode model, right? Why is that? Because I'm actually in the reverse mode here, right? So only when I put a reverse voltage, which is going to be in the same direction as this negative Zener voltage, then the diode will conduct, then the Zener will conduct. Okay? So here is what's happening in the Zener. So this is a typical Zener characteristic exploded. And there are some terms that we need to know here. So this point here and this voltage here. So this is called the Zener voltage, VZ. So this is what this is a parameter that you're given in the datasheet. This is the Zener voltage that you will use to, for example, create a 6.8 volt regulated voltage at the output, for example. This is V Zener, this is V0, VZ0. VZ0 is a result of what? Is the intersection of this V Zener voltage with your current characteristic in the reverse direction intersect at a point where the current is called I Zener test, IZT, the test current. So the intersection of this vertical line with this horizontal line with the characteristic is called the operating point of the Zener, right? Beyond which, what happens? Beyond which I have avalanche. You will be given on the datasheet. So here, this is the datasheet that you have. So these are typical Zener diodes. They will give you VZ at IZT. So the Zener voltage at the test current. So they will give you that. They will also give you the magnitude of the test current, and they will give you also some impedance. Okay, if you remember from our diode, what did we do for the small signal analysis? We found the slope of the IV curve. The slope of the IV curve was equal to 1 over R. R for the diode. Obviously here there will be something similar. We also have a slope, right? And the negative half cycle, and the negative in the reverse bias condition, we also have a slope for that line. That slope will also be the resistance of the Zener. They also give that to you here. Okay? So and then they also give you, of course, a maximum power dissipation, which we talked about before. So there's a maximum power dissipation, so there's a limit to the current. That limit to the power, that you are able to dissipate through that Zener. Okay, so they gave us these. They gave us the V Zener, Oh, they gave us VZK, right? They gave us VZK or no? They gave us VZ. Let's see. I don't remember if they gave us VZ or VZK. VZ. No, they gave us VZ. Did they give us the IZK? They give us also what is called an IZK, and they give us a ZZK. So they give us a ZZ at T, meaning that will be the slope at the test current. And then they give us something that is also the slope, a much higher impedance, right? And that will be the slope at the knee. And this is the current at the knee, right? And then the test current is much higher, right? So let's look at what they gave us. So they gave us the current at the knee. This is IZK. And they gave us the test current, and they gave us VZ, and they gave us two impedances. One of them is this slope here. Remember this again, this is the slope of this line. At this point here, the tangent of that is 1 over r as well, because this is the delta y is delta I, delta x is delta v, right? So that the tangent to this is the slope, has a slope. The tangent to this line has a slope equal to 1 over rz, which is delta I over delta v. So you can take which delta I, you can take is the delta I IZT, which delta v, it's the v zener, right? That's the slope at this line, at this point here. So it's IZT over VZ will give you the 1 over RZ, which is the impedance that they gave us in the data sheet. So from the data sheet, you can actually draw this, right? They gave you this point, and they gave you the tangent at this node. They also gave you this point, and they also gave you the tangent at this point as well, right? So if they give you the tangent at this point and they give you this point, you should be able to also find this point, VZK, the voltage. I think they gave you the voltage at the knee, and the intersection of this tangent here. Yeah, they gave you everything. But they didn't give you VZ0. The intersection of this slope with the horizontal line is called VZ0, right? We will see that now. We will see that. So our model will be as such. Our model will be that the Zener voltage is equal to VZ0 plus some current that we will current multiplied by some resistor here. We will see how we will do that here. But anyway, so we all agree that the slope here will give us the resistor RZ. 1 over RZ is the slope. We're fine with that. Okay, so I can model now. This is in your book. It's chapter 3. The Dios chapter, the Dios chapter, yeah. Right? So we calculated, RZ from the slope of the line, and that's called the increment. It's called the incremental resistance. It's called the dynamic resistance. There are many names for it. And if we look at the curve that we have, we see that the way the one way to model the curve. So we have RZ times IZ, the slope at a certain value of current, plus the voltage is going to give us VZ. So the way to model the Zener diode would be this VZ0 with a series resistance. Right? So there's a VZ0, there's an initial voltage, plus if you start at the initial voltage here, if you start at VZ0, how do you get to VZ? You have to add this voltage drop. This voltage drop is equal to what? This is if you do the geometry, this is a triangle here, and it will have a slope of 1 over r. This has a slope of 1 over r. This will have a magnitude of r times I at that point here. So this is a voltage drop. The voltage drop here is equal to I times r. Okay? It's the current flowing through the Zener multiplied by the resistance of the Zener. So the way we would model the Zener diode is just a resistor in series with a voltage source. And this voltage source also opposes the reverse current flow. Like the diode in the forward direction. Also the voltage source will oppose the current flow direction. Okay? Yes? No? So let's do an application. So here's an example, very similar to the example before, right? Instead of, in the example before, I was using my diode in forward bias condition as a regulator. Here I will use my Zener diode in reverse bias condition as a regulator, right? Same thing, same application. Which is better? Again, at the end of the day, you have to calculate maybe efficiency of this, versus efficiency of that. Do you have the exact zero voltage that you want or not? And we will, effective temperature, etc., etc. But for example, so here's an application. Here's an example circuit. Here you have a resistor and a Zener diode and this load here. So they have you have a 6.8 volt Zener diode in the circuit specified to have VZ at 6.8 and IZ at 5 milliamps. So this is IZ test, probably at this is IZ test. This is your 6.8 volt, and this is your IZ test is 5 milliamps. At these two operating points, right? Remember, these are my operating points, VZ and IZ. These are my operating points here. This is VZ, and this is IZ that they gave you. This is 6.8 volts, and this is 5 milliamps here. And then they gave us this slope here. They gave us what? They gave us RZ is equal to 20 ohms. So RZ equal to 20 ohm, and IZK is equal to 0.2 milliamps. Right? This is 0.2 milliamps. So this is VZ0 here, and this is VZK. We don't care about that. Okay, so the supply voltage is normally 10 and then can vary plus minus 1 volt. This is the same as before. And they're asking you to, I guess, look at what are they asking us for? They're asking us, okay, find the output voltage with no load, and then with nominal voltage, and then I'm sure they're asking us to look at, okay, the effect of the plus minus 1 volt change, and then they're asking us to connect the load, and then look at what happens to the output voltage, and they're asking us to change the load, see what's happening to the output voltage, change the load again, see what's happening to the output voltage. If you keep changing the load, what's going to happen? If you look at your Zener characteristics, if you keep changing your load, so you were first starting here. If you now, okay, remember your circuit looks like this, and this is your Zener, right? You initially had a current flowing through here without the load, and that defined, and hence you had a Zener voltage. Now you connect the load. What will this load do? It will draw some of the current. It will draw some of the current, which means what will happen to the current in the Zener? Decrease, right? So if it decreases, how is it performing here? It's gonna go up this curve, right? Do we agree? I mean, this is the 5 milliamps, right? I will calculate the current that will be close to, this is the original operating point, for example, right? And then I keep adding loads. These loads will keep drawing currents. Keep drawing currents will be pushing my operating point higher and higher. Until when? Can I operate as a Zener beyond? Zener means what? Huh? Someone's last name? No, it's not somebody's last name. Seriously, what am I doing with the Zener diode again?
It's like an iPhone.
I'm regulating the voltage, right? V Zener, if I'm operating around the operating point, that means I'm regulating the voltage, right? The application is a voltage regulation application, right? But if I move from here all the way to here, am I staying around 6.8 volts? I'm not staying around 6.8. I'm losing my regulation. So there's a window here of reasonable regulation, right? You will accept a reasonable amount of change voltage around the V Zener, right? But then if you keep adding loads that draw more currents, they will be pushing this higher and higher and higher. At some point, you get too far away from VZ and you're not regulating anymore. Right? This is not operating in V-Zener. At this point, are you operating in Zener breakdown mode anymore? You're not. Breakdown mode means you have Zener breakdown mode. You have a certain voltage window that you are within around the V-Zener voltage, right? So that's what the example is doing basically. So let's see how they are doing that. And it's very similar to the one before. Okay, we'll calculate the current in the chain in the Zener diode without a load. And then we keep drawing a load and see the effect of that load on the current flowing through the Zener and the drop across the Zener. Yeah. So the model of the Zener diode, we inserted the model of the Zener diode here, right? That's the VZ0 and that's the R Zener. First, I don't have this. What is the output voltage equal to? The output voltage is equal to the current flowing multiplied by this resistive drop plus this VZ0. Now I add a load. Current here will decrease, which means that my output voltage will be equal to VZ0 plus R Zener. This drop will decrease. At some point, you are drawing more current than what's possible to go through here. Yes, ma'am.
Does the value of VZ not change when the...
No. VZ naught is the. It will change where you are in the curve. Yes, because VZ naught we said is what? Is the intersection of. Actually, let's go back here instead of drawing it. Yeah. VZ naught is this operating point. The slope at this operating point, or the line tangent to this point here, is intersecting the horizontal line at VZ0. So every time you go up, VZ0 will change a little bit. At some point, VZ0 becomes what? If you're operating here, where is the slope? Right? It's going to intersect very far away. So you're not gonna be regulating anymore. Right? So that's what's happening. You're moving up. Here, VZ0 is changing, and what's happening also? The current is decreasing. So your VZ0 is decreasing, and your I times R is also decreasing. So at some point, you're very far away from VZ, which is your regulating voltage requirement, and that's it, you're out. You're no longer regulating it, okay? So that's what's happening, and let's see the example. So they solve, so first, first we want to calculate the current flowing this Zener diode without any resistance, without any load. So it's equal to what? The 10 volts, my VCC voltage, right? Minus what? Minus the Zener voltage, because again, open circuit now. I will have to assume something to start with. I will assume it's regulating at 6.8. It's a 6.8 volt Zener, it's open circuit. Right? I'm given these characteristics from my data sheet. I'm giving this information.
They are at 6.7.
6.7 is VZ0. Yeah, it's regulating at 6. So 6.8 is the VZ0 plus R0 times the current. Right? So first we must determine the value of the parameter VZ0 of the Zener diode. Why? Because we want to build the model. Right? So for you to build the model, this is the model that we have. You have to find VZ0 and you have to find RZ. They gave you RZ as 20 ohms. Right? What is VZ0? VZ0 is something we can find from this circuit. It's this voltage. Forget about this branch. This branch does not exist. I'm given this voltage. I am given this resistor value, and I'm given the current. I'm assuming it's 5 milliamps. Right? IZ is 5 milliamps. So in that case, I can calculate at RZ is 5 milliamps, which yields VZ0 is 6.7. So if you just have the VZ0, if you have what? You are given, you're given VZ is equal to, so this is VZ, it's 6.8 volts, this is 6.8, and you're given this as 20 ohms, and you're given this as 5 milliamps. What's missing here? VZ0. VZ0, they calculated that as 6.7 volts, right? Well, it's given because you're given 6.8 and you're given RZ, so that's a given. You can consider it given, right? And then what? Then now I take this Zener. So this is my Zener diode. right? And now I'm gonna see how it's operating in this circuit that they're giving me. Am I really running at 5 milliamps? I don't know. They gave me a condition. They gave me some characteristics of the Zener diode. From the characteristics of the Zener diode, I was able to calculate VZ0 because it's not in the data sheet, right? This is something that's not in the, so I was able to calculate that VZ0. Now I take this model and plug it in my circuit. My circuit here has 10 volts. Resistor here, some R I think was 1 kilo ohm, right? 1 kilo ohm? 0.5 kilo ohms, so 0.5 kilo ohms. And then I have my VZ0, and then I have my RZ, which is 20 ohms, right? So this is my model without a load. There's no load connected here, right? Now you would need to calculate the current flowing through this system. The current is what? This voltage, 10 volts, minus VZ0 divided by R plus R. That's what you have here, right? And that gives us 6.35 milliamps. So it's a little higher than our current that was given originally. That's fine, but which is okay. The output voltage now. So initially we assumed that VZ was 6.8. Is this really 6.8? Is it really 6.8, or is it going to be a little bit more because the current is a bit different, right? So here's how you would calculate that, right? This is the output voltage here in this case. Now after you place the Zener in your circuit, originally the Zener was not in your circuit. They're just telling you that this Zener has a characteristic of 20 ohms at 5 milliamps and VZ equals 6.8. So you calculated V0 outside the circuit. Now you plugged it in the circuit and you want to see, okay, what is the voltage across the Zener diode really in that circuit? So it tends to they use the equation that we were given from the model. So you took this model, plugged it in here, and this is my V output now. V output is equal to what? VZ0 plus the voltage drop across this resistor. Now this voltage drop is influenced by a higher current. So that's why the Zener the output voltage is 6.83 volts. Okay? Yes.
VZ0 before, like they used the same equation to get VZ0 before adding it to the circuit.
Because this was outside, yeah. They told you that I give you a Zener. It has a Zener voltage of 6.8 here. This is my Zener I give you. Shown here. Because you're given VZ, you're given 6.8 volts. You're given 20 ohms, and you're given 5 milliamps. You're given 5 milliamps. So the only thing missing is this. So the voltage drop here plus the voltage drop here is equal to 6.8. And you know that this voltage drop is 5 milliamps times 20. And you know this is 6.8. So you just find this. Okay? So this is this first case. Now they're going to ask us, okay, to plug in loads. These loads are going to do what? Remember, you are regulating your voltage. If you're operating around the Zener operating point, then your voltage is regulated. So if I add a resistor here, what is the current flowing through that resistor? 6.83 divided by the value of the resistor. Right? Because you're regulating the voltage. Or you can use 6.8, it does not matter.
But doesn't
What?
when we're adding a resistor, doesn't the voltage across this change as well?
Of course.
The current?
And that's what's going to happen here. So
Yeah, but why did you take 6.8?
I can add 6.8, it's fine. Again, it's all because you will have to, again, you can solve this graphically or you can iterate. But for example, let's because this was an open circuit. Now current will flow. I need to find out what's going to happen. So I was here. This is my Zener characteristic, right? I was having what I was having 6.35 milliamp flowing in my Zener diode. Right? Now what do I have? I will have some current drawn here. This current drawn here is equal to what? Let's say it depends on the load. So let's say initially they gave us a load of what? 2 kilo ohms. So 6.8 divided by 2 kilo ohms, some current, right? So I will have a current. Let's say 2 milliamps, for example. We will look at their numbers, but let's say 2 milliamps. So what happened to the current that's flowing in my Zener?
Decreased by 2.
Decreased by 2 milliamps. So I have to go back here and decrease by 2 milliamp, and I will have a new V Zener. Right? So I will have a new V Zener. I will also have a new VZ0. how far is this VZ0 from my original Z0? If I'm already operating in my narrow range, on the in the Zener, within the Zener range, then the slope, does it change much really from this point to this point?
No, it's
Doesn't change much. So VZ0 will not really change too much. So you can keep this VZ0 here. And you have this RZ will also be the slope, defined by the slope. So you can also keep this 20 ohm. Right? So if you kept this and you kept this, then really you can use your 6.83. Right? It's fine. Only when only when the current changes significantly, okay, then you have to start thinking, okay, then how far am I away from my original point? Yes, go ahead.
In the lab, we had an equation where we had the summing amplifier and we offset the voltage by 200 millivolts, and it was already distorted, even though we offset it by a little bit. So, does this have anything to do with this? Like,
No, this is
This-
op-amp, this is
so this,
diode.
you say you offset it by a little bit.
Yes,
and
but
it doesn't matter.
if you look at the curve, yes, because if you look at the curve here, what I was drawing is not a very nice curve, but look at the curve here, okay? Change the current. What's happening? There's a very abrupt change from Zener mode to non-Zener mode because of this, because of the fact that this slope, the slope here, is very similar to 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 the slope here. There's an abrupt change in slope around the knee. Before that, the slope is very similar. So if the slope is similar, what does that mean? It means that VZ0 is not changing and RZ is not changing. That's what it means. Do you agree? Right? RZ is basically 1 over the slope. So if the slope is not really changing here much, not much, then what's happening? Then I'm not changing VZ0 at all. And I'm not changing RZ. That's the conclusion here. That's why you can assume that VZ0 and RZ are the same. Now, current was flowing in VZ0 and RZ. What is the output voltage here? This is the output voltage, right? This is RZ. The output voltage here will now depend on this current, right? If the current here decreases, this is fixed, VZ0. So the only thing that will change is the voltage drop across RZ. The voltage drop here is equal to the current flowing through multiplied by the resistance, so I times RZ. This current will change with the change of this. So if this decreases, if this is 2 milliamps, this will decrease by 2 milliamps. This is 3 milliamps, this will decrease by 3 milliamps, which means that the voltage variation will be what? Equal to the decrease in current here multiplied by this resistor, right? So the change of voltage will be due to the variation in current in the output. Until when? Until when I'm drawing all the current into my load here, and I'm moving what? I'm decreasing the Zener current. I keep decreasing the Zener current by drawing more load. Keep decreasing the Zener current. What happens at some point? Finish. At some point, I cannot regulate. VZ0 changes considerably. I'm not regulating. I'm not at my Zener voltage, close to my Zener voltage. I'm very far away from my Zener voltage, right? So, and that's what's happening in this example. It's okay as long as you understand. It's fine. Yeah. So, that's what the example is doing. I will not go in too much detail. I mean, follow it, and then here I'll just show you that they're saying that the change in voltage is equal to the change in current through the Zener diode multiplied by the resistor. This change in current is equal to what? Is equal to the current due to the load. So here I added the load resistance of 2 kilo ohms. This 2 kilo ohms, you take 6.8 volts. Remember, we assumed that we're around the Zener voltage. So we assumed that we're around Zener voltage divided by 2 kilo ohms. I got 3.4 milliamp. This 3.4 milliamp is going to be reduced from my RZ. So the change across the Zener output is going to be the 3.4 multiplied by RZ with a negative sign, meaning it's reduced. Until when? Until at some point, if I keep drawing more current, I lose regulation. So here, they give another resistor where it works, and then they give you 2 resistor values where it works, and then they give you a third resistor value where it doesn't work. So here, so at RL is equal to 0.5 kilo ohms, right? What is the current that you're drawing into the load? It's 13.6 milliamps. Okay, let's go back to our original no load condition. Our original no load condition was 6.35 milliamps. So I had 6.35 milliamp going from my source through my Zener diode at no load. Now my load is requiring 13 milliamps. Can I provide that? The source can provide that, but it means that the current flowing through my Zener diode is 0. So if that's the case, then what does the circuit look like? The circuit looks like my 10 volt source. This is my Zener, right? But there is no load, there's no current flowing through my Zener. So it's like what? It's like an open circuit. Like an open circuit here. And I have my load resistance here that they gave us. Then this is the new R that they gave us. In that case, what is the voltage at the output? Voltage divided between this resistor value, which is R1, I think it was half a kilo ohm, and then this new resistor value that they gave us. Okay, it happened to be also half a kilo ohm, so the voltage here is going to be 5 volts. Am I close to 6.8? No. 6.8 was my Zener voltage diode, Zener diode's voltage. I'm very far away from that, and I'm no longer getting the benefit of the Zener action that I used to benefit from. Okay? So this is the Zener diode in a nutshell. And again, like it's a diode, so temperature does have an effect. You remember all the mobility, holes, electrons moving, so temperature has an effect. So Zener diodes happen to have what is called a positive temperature coefficient. Low voltage Zener diodes happen to have a positive temperature coefficient, meaning their voltage increases with temperature. So if you buy a 6.8 volt Zener, it has a VZ0 of, it was 6.7, right? At a certain current, for example. This VZ0, if you increase the temperature by 1 degree Celsius, the VZ0 may go up by 2 millivolts, right? Plus 2 millivolts per degree Celsius, right? So these Zeners have a positive temperature coefficient. Remember, our diodes had what? A negative temperature coefficient. We used to be able to use them as a temperature sensor, right? I can also use this as a temperature sensor, since the voltage drop across it is changing with temperature as well. So I can also use it as a temperature sensor. But mainly the Zeners are used for voltage regulation. So one application they describe here is an application where you want to regulate the voltage to a certain value, for example, and you chose your Zener, you put your Zener diode here, and temperature changing. So you know that this Zener is a positive temperature coefficient, right? And you want to create a stable voltage source regardless of temperature. So one way to do that is also put a diode here that will operate in forward mode. Diodes have a negative temperature coefficient. You can find a diode that has a negative temperature coefficient equal to the positive temperature coefficient of the Zener diode. So one changes by plus 2 millivolts per degree Celsius, and the other changes by minus 2 millivolts per degree Celsius. And that way you can create a regulated voltage here that is independent of temperature. You can create a regulator like this. This is a temperature independent, temperature dependent regulator. And the regulated voltage will be here what? Equal to what? You have to look at the model. The model of the V-Zener is what? VZ0 looking this way, and this is the diode. Diode is going to have a forward voltage, so this is the current flow. So I'm going to have a forward voltage opposing current flow. So the model of these two together, when current is flowing, looks like these two voltage sources in series. This is going to be 0.7, and this is going to be whatever Zener voltage that you have, 6.8. Because one is operating in forward mode, and one is operating in the reverse mode. One is opposing negative voltage, so the voltage is opposite the other one. Okay? So here, what is the voltage here? 0.7 volts plus V Zener that you chose. Right? It's just an application of the Zener diodes here. Okay. We talked about rectifier circuits. I will skim through this quickly. So we talked about rectifier circuits at the beginning of the chapter as a motivation for applications of diodes. The one thing we didn't include when we talked was what? I said that this diode was ideal. I just modeled it as an open circuit or a short circuit. But in reality now we know that we have to include Instead of the short circuit model, we have to include a voltage drop, right? So what is the output voltage going to be? The output voltage will be what? This is my circuit now.
Vs
Yeah?
minus VD.
Yeah. Vs minus Vd will be your output voltage when the diode is conducting. Vs minus Vd is the output voltage, exactly. Right? So that will be the
Don't you have
output.
to do the resistor, the voltage division with the resistor though?
No, it's a source. It's
Oh,
two
for
sources and a resistor here. What is the output voltage?
Oh,
So what is the voltage across the resistor? It's Vs minus Vd.
sorry.
Right? So that's the output voltage across. And what is, when it's in the open circuit condition, what is the voltage across the diode? In the open circuit condition, what is the voltage across the diode?
Vs.
Vs. Right? So you would have to buy a diode rated for a little bit more than Vs, of course, to plug it into this circuit, right? And we figured out what the output voltage is. So the output voltage, instead of looking exactly like the input for the whole positive half cycle, it will look like the input minus Vd, right? You always subtract Vd from it.
But
Yeah.
if you look at that, isn't that like
Right? It's very small.
inefficient of some sort? It's gonna be
Of course,
0, 1.
this is loss. Yes, this V forward is a loss. Yes, it's inefficiency. Yes, sure. It's a loss. You have something opposing you, and this something is a voltage source, and you're pushing current through it. So voltage times current is power loss. Yes, it's a loss. It's a diode loss. It's called diode conduction loss. Exactly. In 438 we study that in a lot of detail. Yeah. So it's called diode conduction loss. Here we will just look at some of the waveforms as a motivation for applications of diodes. But we're okay with the waveform now? And then, so this is and again, we said that the peak inverse voltage is Vs, the blocking voltage that we just discussed, okay? Another application is this is called a half wave rectifier before. Now, another application is called a full wave rectifier. In a full wave rectifier, think of this as the following. Think of this as two sources. Think of this as a source here, another source here, Vs, another Vs source here, and one diode here, and this is your resistor.
And that's how they
This is what? By itself, like if you look at this is like what? Like the half wave rectifier we just discussed. This is just a rectifier.
just add another.
And then now I create another one, but instead of the diode looking this way, I make the diode look the other way. So, I mean, it's not, I'll show you what I'm doing here.
Okay.
In the positive half cycle, what's happening? In the positive half cycle, this
It's
voltage
creating a
is
half.
positive, right?
That's like
And then, I mean, I have positive voltage. This is positive voltage, right? It's positive voltage. If it's positive voltage, this diode will not conduct. This diode what? This diode wants to conduct when? If I put a voltage like this,
When Vs is 0. Oh.
right? This diode this bottom diode here wants to conduct when this is more positive than this.
But don't the voltage sources have to be in different phase? Cause that
No. The voltage. This is a transformer. Transformer. It's called a center tap transformer. So that's why you can model it as two series voltage sources that are identical. In the positive half cycle, it's like having two positive batteries. It's like having two positive batteries, like this. And then this. Right? Two positive batteries. Is this diode going to conduct? Okay, well, let's look at the circuit. In this loop here that I have, this is the loop here that I have for this diode, right? It's a loop, right? It's KVL around this loop, right? In this loop, this is the most negative potential. It's connected to the anode. So anything else in the circuit is going to be more positive. So this diode will not conduct when the voltages are in the positive half cycle. And this diode will conduct because this is positive with respect to this node. What? If I flip the sources and I operate in the negative half cycle, what happens? If I flip the source, if I flip the source and operate in the negative half cycle, sorry. Now the bottom diode is, its anode is connected to the positive terminal of the supply, the other one will not conduct. Right? So it's like having, right, do you agree? The top one will not conduct here. This is the loop here. Yeah, one will be on, one will be off, depending on the half cycle. So I actually have, it's like two half-wave rectifiers back to back.
So they're not turned on at the same time?
No, they're not turning on at the same time. One, this top one is giving me this one.
Okay, that's why I said it was like...
And the bottom one is giving me this other half-wave.
Okay, that's why I thought it was in different phase, because...
No, the center tap transformer is a bit confusing. Yes, I agree. But
I didn't do the test.
I don't know. I didn't make the test yet. But this is called the center tap transformer with a center tap rectifier. And this is, the nice thing is, what I bought myself here is my output now is full wave. Remember, output, if I want to deliver power, excuse me? It cannot be negative. Because current, look at this. That's a good point. Current is going to flow this way into the load, right?
Yeah.
Also, current will flow this way into the load. Is the output ever going to change polarity?
No.
No. The output will never change polarity because you never change the direction of current flow in the resistor, which is your output voltage here.
We have like cases where we have like two diodes that are off.
This, no.
Not this.
Not this one, the next one. Next one. And here, okay, just quickly before we move on, what is the, just so that we can, what if one is on? If let's say D1 is on. Yes, let's say D1 is on, and I'm in the negative half cycle, and D2 is off. When D1 is on, the model for it when it's on is what? Current, voltage source opposing. That's equal to VD, right? And this is VS, and this is VS. This is off, so it's an open circuit. So what is the voltage that you have to buy this diode rated for? VS and VS minus VD. So it's 2 VS minus VD is the voltage across this diode. Same thing with this one when the other one is on. So this, in the half-wave rectifier, the rating of the diode was what? VS. Only VS. In the full-wave rectifier with the center tap, I used 2 diodes, and I got much more waveform, which means more power. I doubled the amount of power that's going to be at the output, but I have to buy higher rated diodes. There's another full-wave rectifier that takes, figures out this problem with the double the voltage around on the device. So it still gives me a full-wave rectifier output. And how does it work? Let's look at what's happening. If this is positive with respect to this, that means current will flow here. It cannot flow in here, right? It can flow in here, it flows into my load, and then current has to come back from where it came from, right? So, yeah, it does. This is current. This is the rule, yeah, right? So it's not going to go through here. It will actually go through here. So in the D3 is going to happen in the negative half cycle. So in the when this is more positive than this is the way the current will flow. How about when?
So D3 is open.
Yeah, D3 and D4 will be open. So what is the voltage across D3?
But I thought a transformer made DC energy.
It's what? 1 second. It's the V output. No. This is current flowing here, so this is the voltage drop. And this is current flowing through here, so the diode voltage drop is this way. So the rating for this diode is what? Is V output, which is what? V output, which is equal to Vs, right? So it's V output, which is equal, so here, so the rating for this, the rating, so this diode is, this is on as well, so if this is current flowing this way, then this is voltage in the opposite direction. So the voltage on the resistor is what? Vs minus Vd. V output, which is the voltage on the resistor, is equal to Vs voltage minus Vd. That's V output. Vs minus Vd. How about the voltage on diode 3? Because that's the one that's open now. It's equal to V output plus VD. Yeah, because this is in the same direction as this one, right? So in that case, Vs minus 2VD. Vs minus what? Vs minus VD plus VD. So it's Vs. Oh, no. Why am I doing? What am I doing? So it's Vs plus VD. So it's Vs minus VD is the V output. Okay, let's see what's happening here. So this is Vs, right? And I'm moving this. This is Vs here, and this is Vs minus. Current is flowing in this direction, so VD will oppose it. So VD is this one. So this is Vs minus VD. This is V output. So Vs here minus VD1, right? Minus V output minus, right? Minus VD2 equals 0, right? Do you agree? One second. So I want to calculate V output first because this is wrong. I want to calculate V output. So what is V output? And then remember, VD1 is equal to VD2. So it's actually Vs minus 2VD, which is a diode voltage drop, minus V output equal to 0. So V output is equal to Vs minus 2VD. Right? And VD3 is V output plus VD. So VD3 is equal to V output, which is Vs minus 2VD plus VD. So the peak inverse voltage across the diode is Vs minus VD, right? And that's what we have here, Vs minus VD. So you believe me, that's good, yeah. Okay, so that's the full wave rectifier. Huh? في it's the rectifier with the filter capacitor. I think this we will cover this in 438 in a lot of detail. So basically the idea is if I have a capacitor, okay, capacitor is like a so we had the half wave rectifier, right? The half wave rectifier gave me this half wave output, right? But now I put a capacitor and I didn't put a load. What's going to happen? When you put a capacitor, when this diode conducts, I'm putting this capacitor across my source. So what's going to happen to the capacitor voltage? It will be equal to the source voltage. At this point, my capacitor's charge is equal to this peak voltage, right? And then my source voltage is going down. This capacitor voltage will not change. There's no current coming out of the capacitor to bring the capacitor voltage down. So what's going to happen? The voltage on this side of the diode, the voltage on this side of the diode will be
Would it create like constant?
larger than the voltage on this side, because this has been charged to V peak. When the diode was on in the first half cycle, it's charged to V peak. Then so I have V peak here. This guy wants to go down. This input source voltage is going down, right? So is the capacitor voltage going to go down? Capacitor voltage will go down when you connect a resistor across it. Then this resistor, first you were charging the capacitor this way. Current is flowing into the capacitor.
Isn't it going to discharge though?
If it will discharge if you have a resistor. If you have no resistor, it will not discharge.
The diode, don't we need the more positive
Oh
side?
yeah. Oh, that's pretty cool.
Yeah, for the diode to conduct, you need the most positive side on the left, yes.
So it will not
So in the first half cycle, it will conduct.
Okay.
And then you charge V capacitor to V peak. On this side now, I'm going down. The source voltage is going down. This capacitor voltage is not going to fall down. So since it's not going to fall down, then this voltage will be higher than the voltage on this side. It will stop conducting. And it will maintain V peak forever. Of course, this is not very practical. I want to put a load. So if I put a load here that's small, what's going to happen? I will do what? What's going to happen? What do you expect to happen?
Why wouldn't you want that output to be a straight line though?
No, you want it to be a straight line. But if you you always have a load. I mean, if there's no load, you have a power supply but no load. Ya farhati, it's not useful, right? It's not, what's useful here? You have power here, an outlet here. Okay, cancel it. We're not using it. right? Why did you pay for it, right? So you typically have a voltage source, so you can load it, right? So since that's the case, we will have a load here. Using the same logic, right? When the diode conducts, you're putting the voltage source across the capacitor. Nothing will change in the first half cycle. Until here, we're fine. Now what happens is interesting here. If I put a resistor here, what's going to happen to the capacitor voltage?
And big space limit.
You know, capacitor voltage will drop based on the value of current that's flowing here. If I choose this resistor wisely, so that I don't drop this fast, then what's going to happen? Then I will drop a little bit. I will keep dropping a little bit. How is this drop going to be governed? By an exponential, remember? It's an RC circuit, 214, right? It's an RC circuit. It's governed by 240. It will fall. It will fall until when? Until my input voltage here starts rising again. It rises again. It hits. They're equal. Equal plus. So as soon as this becomes a little bit more positive on this side, the diode starts conducting. Charges the capacitor again. Then we go through the same cycle. Capacitor starts discharging.
And this is useful.
And this is very useful. Okay? So we'll stop here. This
Are
is.
we gonna finish chapter
Huh?
two on Sunday?
The quiz is on Sunday.
Are we gonna finish it?
No, we're not finished this chapter. I think that this is the last thing in the chapter actually. So we talked about this, but I'm not going to talk about its equation. You understand this? In 438, I cover this in a lot of detail. So
There's the super one.
no, we're not going to talk about the super diode. No, it's fine. But I want you to look at this, okay? No, 1 second. But it's not new material, okay? It's not new material. Look at these circuits. We talked a little bit about something like this, right? We talked about putting a Zener in series with a diode, right? So these are different configurations. Make sure you understand those.
Oh, okay.
It's on page. It's it's called the limiters and clippers or something like that. Limiter circuits. This is not new material. Just go through it, and if you don't understand, it's what we did an example where we put a Zener with a forward diode. We did one example like that. Here they give you a lot more examples like that. And they're just applications. If you want to control the regulated voltage at certain levels using different components, how would you do it? So go through these, and this is really the end of that chapter. Really, I mean, we covered everything in the chapter except the equations of capacitor rectifiers, which we will cover in 438 in a lot of detail. So we're done.
Something so.
Almost done. I think.